Hello, welcome back. Alright, so we just did a bunch of Beyond Bohr stuff. I'm going to give you just a tiny smidge more Beyond Bohr and then get you a lab and your spectra and stuff. So a little more Beyond Bohr. And these are just two other sets of thoughts that we've had. Beyond Bohr Part 2. I just want to introduce you because you probably I shouldn't tell you what you've maybe heard around other places, but it's just kind of funky stuff. Okay, so, and these are just two of the many other humans who researched things. Berkeley figured out all particles have some wave characteristic and some mass characteristic. And some mass characteristic. So if you've heard of the... Oh, you didn't even see me spell that wrong. That wasn't even on the screen. Okay. I messed up characteristic. If you've heard of the wave-particle duality... that is a thing. All things, I would say all physical things, all physical things have some attributes of a wave and some attributes of a particle. You are a big thing relative to an atom. You are more familiar with the particle aspect of things. So if I was to say, is this writing utensil a physical object or a wave, you would probably look at me like I was nuts and tell me it was a physical object. If you were to look at your friend or whoever you are nearby these days, or your wall, for that matter, and say, is this a physical object or is it a wave? You would say it's a physical object. Little do you know that all things have some attributes of both. So you have a waveform. You are an object with a large mass. You are primarily characterized by your particle aspect nature. However, you also have a waveform, which can be calculated based on your mass, which is kind of wild. And things with really small mass, small mass and high energy, can kind of blip in between being mass and being wave, their mass form and their wave form. So we're talking really hot kind of star stuff can go between wave form and particle form. This was a similar time and similar idea of this, which we're not going to take too deep in this class, but super related ideas. Here's the energy. Energy you can measure as a wave, and here's your mass. You can convert mass into energy and vice versa, which is wild. So again, we're not gonna go real deep. And you're probably like, okay, cool, I got E, I got M, I know what 2 means, but why is C in this equation? So C is the speed of light, which is big, by the way. Light speed, right? Okay, so speed of light. So what this means is that mass has a whole lot of energy, basically. You have to have something very hot to actually blip it between its wave form and its mass form. One place that's happened there's so much we could get into here that we're just not going to, because I'm going to try to keep this somewhat short as a video. But yeah, this was some of the research into like atoms that has happened since Bohr, that I think is cool. Just kind of describe. The other one that's also cool. This is a name of a human, again, who did research, and we commemorate this individual because they came up with which doesn't necessarily seem like something we want to be commemorating somebody for. They came up with the idea that we don't know some stuff. But it's kind of fascinating that this is also like kind of critically important groundwork. When you get into nuclear chemistry, you wind up calculating uncertainty, which is wild. The first time I read a question that was like, describe, like calculate the uncertainty of this particular thing. And I was like, I don't think I can, thank you. But I figured it out. Don't worry, I got there. And it has to do with the distance between two things. As the distance between two things decreases, the uncertainty increases. And as the distance decreases, the uncertainty of the momentum. Okay, what's momentum? Think of it like speed and position and stuff like that. So it's impossible to know both the location and the path of the electron. So it's to know both the location, which is kind of like this decreasing box. We think of it as a box. Like if we know one particle is in this box and we're looking for, is the other particle there also? So we can't know both the location and the path of an electron. Because looking at it moves it. The energy that we would send in to look at the electron. Atoms are way bigger than electrons. This is like super tiny stuff here. But the actual energy that we would send into the system to try to look at the electron moves it, and now we don't know where it is anymore. So as we try to zone in on exactly the location, we change the path. If we try to know the path, then we know where it might be, but not where it is. Great. Also not going deep here. But what this kind of stuff has shifted us towards is instead of trying to identify the location of an electron, we will try to establish where it might be. Yeah, I mean, we're talking quantum, right? So like, it's in this realm. We no longer know with certainty where it is. We're going to say where it probably is. Oh boy. Okay, so now, what did I just say? We don't know. But we know where it might be. We know where it probably is. We call it the probability of where it is. We know where it... its probability of being somewhere. And you may be thinking to yourself, just last week you took something that I learned in middle school and like slightly complicated it a little bit, was just making me write extra words, and now suddenly we've gotten into quantum leaps. Quantum leaps just means from one energy level to another energy level. Like if you were to make it to the ceiling, that would be a quantum leap, except that you're macro, so like it's not. But like for electrons, a quantum leap just means jumping from one energy level to another energy level. That's your quantum stuff. And I'm gonna introduce you to this concept of probability being not where the electron is, because we're not sure on that point, but we know where it probably is. Oh, that's a cliffhanger. I mean, maybe it's not a cliffhanger. So tomorrow we'll draw some pictures of what probability atomic, like, don't worry. Let's do tomorrow. Let's do today. I'll make another video of exactly what you're doing for homework, but you're probably, get it, probably, gonna be watching a lab and describing what you see and looking a little bit at some element spectra. Enjoy, let me know your questions, and see you soon.